Can black holes collide with each other? In the history of the universe, has that ever happened? And if two black holes really do meet, what happens next? There is something strange about this. When we think about a collision, we think of fire, explosion, and matter being torn apart. But a black hole collision produces none of those things. There is no light to see. There is no matter to explode. So where does the energy of this event go? The answer is not inside the black holes. It lies in space-time itself. And to understand that, we have to start with the most basic question. What exactly is space-time? In everyday thinking, we instinctively separate the universe into space and time. Space is where things exist. Time is what flows, ticking forward independently of everything else. This separation feels natural, almost obvious, because it matches how our senses experience the world. But modern physics tells us this picture is incomplete. Space and time are not two independent stages running side by side. They are deeply intertwined, fused into a single structure that governs how reality itself behaves. This unified structure is what we call space-time. It is not just a convenient mathematical idea. It is the actual framework in which every event in the universe takes place. Any event needs more than a location. It also needs a moment. And more importantly, the relationship between events depends on both at once. You cannot fully describe motion, causality, or change using space or time alone. To understand why space-time can vibrate, we need to abandon another deeply rooted assumption. We tend to think of space as an empty container, a passive arena where matter and energy simply exist. In reality, matter and energy do not merely exist inside space-time. They actively shape it. They tell space-time how to curve, and that curvature tells everything else how to move. What we usually call gravity is not a force pulling objects through space. At the deepest level, it is the geometry of space-time itself. Objects follow the straightest possible paths in a curved structure, even if those paths appear bent to us. This is why planets orbit stars, and why light bends when it passes massive objects. Nothing is being pulled in the traditional sense. Everything is responding to the shape of space-time beneath it. Once we see space-time as an active structure rather than a passive background, a crucial implication follows. Any structure that can be bent can also oscillate. Any framework that can deform can also carry waves. Imagine a stretched fabric. When nothing disturbs it, it remains still. Place a heavy object on it, and the fabric curves. Move that object suddenly, and ripples spread outward. Those ripples are not objects traveling across the fabric. They are vibrations of the fabric itself. Space-time behaves in a similar way, but across 4 dimensions and on cosmic scales. When mass and energy change slowly, space-time adjusts smoothly. But when massive objects move violently, the structure cannot remain perfectly stable. It reacts. That reaction takes the form of vibrations propagating outward. These vibrations are not made of particles. They are distortions in the geometry of space-time itself, traveling through the universe at the speed of light. Not every motion is capable of producing such vibrations in a meaningful way. Everyday movements change space-time too, but the effect is unimaginably small. To generate significant ripples, the universe demands extreme conditions. Huge amounts of mass must move at tremendous speeds. Enormous energies must be concentrated and rearranged in very short periods of time. Only then does space-time respond with waves strong enough to travel across cosmic distances. When we say space-time vibrates, we are not describing something happening inside the universe. We are describing the universe itself changing shape, however slightly. Distances stretch and shrink. Time itself ticks a little faster, then a little slower. This reveals something profound. Space-time is not an abstract idea. It is a physical entity with elasticity, dynamics, and limits. And like any physical system, when pushed hard enough, it responds, which leads us to an inevitable question. If space-time is the fabric underlying all of reality, what kind of event is powerful enough not just to bend it, but to make it vibrate across the universe? If space-time is a cosmic fabric, what can possibly shake it? Few objects in the universe are as misunderstood as black holes. In popular imagination, they are often described as cosmic vacuum cleaners, devouring everything nearby with an irresistible pull. This image is dramatic, but it is deeply misleading. It suggests that black holes possess some special, mysterious force that ordinary objects do not. In reality, the truth is both simpler and far more profound. A black hole is not defined by what it pulls in. It is defined by what it does to space-time. It is a region where space-time is curved to an extreme, beyond anything produced by normal stars or planets. To understand this, we need to let go of the idea that gravity works through invisible tethers or pulling forces. As we saw earlier, gravity emerges from geometry. Objects move the way they do because space-time tells them how to move. A black hole is simply what happens when a large amount of mass is compressed into an extraordinarily small region. The curvature of space-time becomes so steep that all possible paths lead inward. There is no new force acting near a black hole. There is no enhanced gravitational pull in the usual sense. The same laws apply. The geometry is just pushed to its absolute limit. This is why a crucial thought experiment reveals so much. Imagine replacing the sun with a black hole of exactly the same mass. The sun disappears, but its mass remains unchanged. What happens to Earth? Surprisingly, almost nothing changes. Earth continues to orbit in the same way, following the same path, with the same period. There is no sudden collapse inward. This single fact dismantles the myth of black holes as universal destroyers. From far away, a black hole behaves gravitationally just like any other object with the same mass. What makes a black hole different is not how strongly it pulls, but how space-time behaves near its center. As one approaches, the curvature grows more extreme. Paths that once allowed escape begin to close. At a certain boundary, called the event horizon, space-time becomes so distorted that all future paths point inward. Crossing this boundary does not feel like hitting a wall. It is simply passing a point of no return. This is why black holes are not violent everywhere around them. Space does not suddenly tear or explode. For most of their surroundings, physics behaves calmly and predictably. The danger lies not in attraction, but in geometry. Near the center, space-time curves so sharply that the very concept of stable motion breaks down. But this extremity is localized. This reframing changes everything. A black hole is not a cosmic monster roaming the universe. It is a natural consequence of gravity taken to its logical extreme. And once this is understood, a deeper mystery emerges. If black holes are not special because they pull harder, why do they become so extraordinary when they interact with each other? If black holes are defined by geometry rather than force, What happens when two regions of extreme space-time curvature collide? If black holes are not special because they attract, then what makes their encounter a universe-scale event? Black holes rarely exist in perfect isolation. Many of them are born as pairs, formed from massive stars that once orbited each other long before collapsing. From the beginning, their story is already a shared one. At first, these two black holes can orbit each other calmly, separated by enormous distances. On human timescales, their motion appears almost frozen, slow and unchanging. But the system is not truly static. Even in this quiet phase, energy is being lost, not through light, not through particles, but through subtle changes in spacetime itself. As energy escapes, the orbit cannot remain the same. The two black holes begin to spiral inward, very slowly at first. Their separation shrinks, almost imperceptibly, orbit after orbit. This gradual inward motion is known as in-spiral, a long prelude that can last millions or even billions of years. It is a quiet countdown written into the geometry of spacetime. But as the distance decreases, the pace begins to change. The closer the black holes get, the faster they orbit. Each revolution happens more quickly than the last. This acceleration is not driven by an increasing force. It is driven by geometry tightening its grip. The curvature of spacetime deepens, and the allowed paths become steeper and steeper. As the in-spiral continues, the system enters a dramatic new regime. The black holes are no longer moving slowly through curved spacetime. They are racing through it. Their orbital speeds climb to extraordinary values. A significant fraction of the speed of light is reached. Not briefly, but sustained over multiple orbits. At these speeds, the distinction between space and time becomes increasingly blurred. Effects that are negligible in everyday life now dominate the dynamics of the system. Time passes differently for different parts of the system. Distances contract and stretch depending on motion. Space-time itself is being stressed to its limits. This is the point where the system can no longer be described as two separate objects orbiting each other. It becomes a single, tightly coupled space-time structure in violent motion. The faster the black holes move, the more energy the system loses. And the more energy it loses, the faster the in-spiral becomes. A feedback loop has begun. What began as a slow cosmic dance now turns into a rapid, unstoppable plunge. The final moments approach, measured not in millions of years, but in seconds. At this stage, the system is storing enormous amounts of energy in its motion and in the extreme distortion of spacetime around it. And that energy must go somewhere. Which leads to the next question. When two black holes are orbiting this fast, where does all that energy escape to? When people imagine two black holes colliding, they often picture a colossal explosion. Something violent, bright, and catastrophic, like the biggest bomb the universe could possibly create. But this intuition comes from everyday experience with matter. Explosions require material to collide, heat up, and be thrown outward. Black hole mergers are fundamentally different. By the time two black holes are about to merge, there is almost no ordinary matter left in the system. No surface, no atmosphere, no fuel waiting to ignite. So when the final collision happens, nothing explodes. There is no flash of light, no shockwave of particles expanding into space. And yet, something extraordinary still occurs. Because while there is no matter to explode, there is something else undergoing extreme acceleration. Enormous amounts of mass are being whipped around at relativistic speeds, not gently, but violently, changing direction and configuration in fractions of a second. According to the rules of spacetime, accelerating mass cannot remain silent. When mass accelerates in an asymmetric way, spacetime itself must respond. That response is gravitational waves, not particles, not radiation in the usual sense, but ripples in the structure of spacetime itself, launched outward from the merger. During the final moments, the distortion of spacetime changes rapidly and violently. The geometry reshapes itself again and again as two horizons become one. These rapid changes generate powerful waves that propagate outward in all directions. They stretch spacetime, then compress it, rhythmically, as they travel across the universe. This is where the true scale of the event becomes clear. In just milliseconds, an amount of energy comparable to several suns is released, not as light, not as heat, but purely as gravitational waves. The universe briefly outshines all the stars combined, without producing a single photon. These waves do not weaken because they spread through a medium. They weaken because spacetime itself expands. Yet even so, they can travel for billions of years, long after the black holes have merged and settled into silence. The ripples they created continue moving outward, carrying a precise record of the event. Every oscillation encodes information about the masses, the speeds, and the final shape of the merged black hole. Spacetime remembers what happened. And here lies the final mystery of this chapter. These waves spread across billions of light years, stretching and shrinking spacetime by amounts smaller than an atom, which raises a remarkable question. If these signals are so faint by the time they reach us, how did humans ever manage to hear them? Gravitational waves do not glow. They do not leave trails in the sky. No telescope, no matter how powerful, I can see them directly. By the time these waves reach Earth, they are unimaginably faint. The violent collision that once shook spacetime now arrives as a whisper. Yet humans found a way to listen, not by looking outward into space, but by watching space itself change right here on Earth. Gravitational waves do not push objects around like wind or water. They stretch space in one direction, while squeezing it in another. Then reverse the pattern. This stretching and squeezing affects everything, including the distances between objects that appear perfectly still. The challenge is scale. The change in distance caused by a passing gravitational wave is smaller than the size of an atomic nucleus. To detect this, scientists built instruments designed to measure distance with almost absurd precision. They do not look for motion. They look for distortion. Laser beams are sent down long tunnels, reflected by mirrors, and brought back together. If space-time stretches even slightly, the returning beams fall out of sync. That tiny mismatch is the signal, a direct imprint of a gravitational wave passing through Earth. But detection is only the beginning. The real power lies in what the signal contains. Each oscillation carries information encoded in its shape. From the rising pitch, scientists can tell how fast the black holes were orbiting. From the amplitude, they can estimate how massive they were. The final ringdown reveals the mass and spin of the newly formed black hole. As spacetime settles into a stable shape once again, even the distance to the event can be inferred. because gravitational waves weaken in a precisely predictable way as they spread across the universe. In a single signal, recorded over fractions of a second, lies the full history of a cosmic collision that happened billions of years ago. For the first time, humanity was not just observing the universe, it was sensing the motion of space-time itself. And for a while, the signals matched expectations. They confirmed theories, validated predictions, and filled in missing pieces, until one signal did not. A signal that did not fit neatly into existing categories. One that hinted at something the universe was not supposed to produce. And with that signal, the story took an unexpected turn. And then, a signal appeared that broke every prediction. For a long time, black holes fit neatly into two categories. Stellar mass black holes formed from collapsing stars, and supermassive black holes anchoring the centers of galaxies. Everything in between was largely theoretical. According to stellar evolution models, nature should avoid producing black holes in a certain mass range. Stars either leave behind smaller remnants or collapse into much larger ones. The middle ground should be empty. This apparent gap was not a mystery. It was a prediction, a consequence of how stars live, burn, and die. And then, a signal arrived that did not respect that prediction. Embedded within the gravitational wave data was evidence of a black hole with a mass that should not exist, too heavy to come from a single star, too light to be a supermassive giant. This object fell into what scientists call the intermediate mass range, a category long suspected, but never clearly observed. Its existence forced a re-evaluation. If stars cannot easily produce such black holes, then something else must be at work. Something that operates over far longer timescales. The most compelling explanation points back to mergers. Not one collision, but many. Black holes growing, step by step. Feeding not on matter, but on each other. Over billions of years, smaller black holes could merge repeatedly inside dense environments. Star clusters, galactic cores, places where gravity constantly brings objects together. Each merger leaves behind a larger remnant, and that remnant becomes the seed for the next collision. In this view, intermediate mass black holes are not anomalies. They are milestones, temporary states in a long chain of growth. What we detected may not be an exception at all. It may be the first clear glimpse of a population we simply lack the tools to see before. If this is true, then black hole growth is not limited by the life cycle of stars. It is an ongoing process written into the structure of the universe itself. Black holes may grow without bound, through merger after merger, reshaping galaxies and space-time on the largest scales, which leads to a final, unsettling thought. If black holes can keep growing by merging indefinitely, what does that mean for the long-term fate of the universe? If black holes can grow without limit, how does the universe ultimately end? Black holes are often described as the ultimate endpoints of the universe, places where matter disappears and time seems to stop. But what we have seen tells a different story. Black holes are not just endings. They are active participants in shaping reality. Each merger does more than combine mass. It rearranges space-time itself. Distance change. Time flows differently. The geometry of the universe is rewritten. In this sense, gravitational waves are not just signals. They are records. The universe leaving behind a trace of its own evolution. Every collision, encodes a story of motion, mass, and time. A moment when space-time itself responded and remembered. And the story may not be finished. Far into the future, black holes may continue to find each other, merging again and again across cosmic timescales. Some theories suggest that this process could go on indefinitely. That structure gives way to larger structures, until the universe itself changes phase. In the most extreme ideas, all of space-time could one day collapse inward, ending not in darkness, but in a final singularity. Whether this fate awaits us or not remains unknown. But what is clear is this: black holes are not silent. They are messengers of the universe's deepest dynamics. If you want to keep exploring places where physics reaches its limits, where space and time reveal their true nature, consider joining us. And perhaps, the next time we hear the universe speak, we will understand it a little better. Because maybe what we call the end of time is not an ending at all. It may simply be how the universe begins a new story.